Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of classical mechanics with the course code PHY 211, we are at the lecture number 14 and the topic is calculus of variations. These are the mathematical techniques needed to derive the Lagrange equations from Hamilton's principle. Hamilton's principle says that the actual path of a particle or system of particles whose dynamics are considered are the stationary values of a line integral of a Lagrangian. In today's lecture, we will learn that how we can use stationary points to derive the actual path of a motion of a particle or system of particles. So to do so, we consider the one-dimensional case for the simplicity, and we define this line integral j, and it goes from point x1 to x2, and this is the function we want to construct, and this is the function of path y and its derivative with respect to x and explicitly the x. So these functions are actually are defined on these paths y is equal to y of x, and these paths goes from points x1 and x2, where this y dot is by definition the derivative of this path, which could be then actual path. We will know that there are methods to know that whether it is an actual path of the particle or if it is not the actual path of the particle, but this y dot is the derivative of this y with respect to x and not with respect to time. So here we have considered the x as a replacement for time, and so it's just a parameter here in this case with respect to which we can calculate the derivatives. So this is the line integral. Now it's a one-dimensional problem. It's not a two-dimensional problem, by the way. It's just a one-dimensional problem. So we consider the particle moving from point x1 to the x2, and this y is actually giving us the paths. In order to visualize this, let's go to the diagram of this, where we will have 2 points, that is the path at x1 will be equal to y1 and the path at x2 will be equal to y2. By this I mean that every path will go through these 2 points. So in order to visualize this, let me draw the x-axis and also the y-axis, and then define these 2 points. So here is a point x1 and y1, and here is a point x2 and y2. So we can construct so many paths, actually infinite number of paths between these 2 points. So let me construct first one. So you can see that this red line is the path 1, which is passing through the point x1 y1 and point x2 y2, but we can have another path over here as well. So this is the path number 2, and it is again passing through these 2 points. So this is the condition that all the paths which we can construct here actually will pass through these 2 points, and there could be another path, and there could be infinite number of paths, but the only condition on these varied paths which we are deriving, these are all the paths which are possible paths, but none of them is actually actual path. We will know that how to construct the actual path from the calculus of variations, but at the moment, just to give an idea that we can have infinite number of paths which pass through these 2 points. So the only condition on these varied paths we are putting is that the starting point and end point, all the paths will pass through these points. Okay, so we have now a line integral which is defined for these paths, and we want to know that our system of particles are a single particle whose dynamics we want to understand actually follows which path. So we want to derive an equation which will give us the correct path for the dynamics of a particle or a system of particles. So this we can do by putting the problem into the calculus of variation, and we will actually construct a path which depends upon the x variable and also another variable alpha. We introduce here a variable alpha in order to make the variations of the paths, and this will be equal to y at x is equal to 0. Here you see this, the value of alpha is now equal to 0, and this will we will know that this will be the actual path, and plus the alpha and some other functions. So these will be the functions of variations, and you see that this is the set of varied paths. So this is not the only one path. Depending on the value of alpha, we will have infinite number of paths, but when alpha will be 0, that is the variation will be 0, then we will get the correct path. So the function this function must vanish at x is equal to x1 and x is equal to x2. As we have demonstrated in the last slide, that at the end points all the paths will pass through the x1 and x2, and at that point these function must vanish because there will be no variation. So all the paths are equal, they are not varying, but in between there will be variations, and the actual path will be or the correct path will be this one, for which alpha is equal to 0. So what we have now done is that we have introduced the calculus of variations and constructed this path y in terms of parameter alpha. So we made it a parametric equation. So let's go back and put this y into the line integral j. So this was our initial line integral where we have defined this function f of y and y dot and x. So now what we want to do is to replace this y and this y dot with the variation with the set of varied paths which we have just defined. So we will get this j now, which is a function of alpha, because this y is a function of alpha, and also the y dot is a function of alpha. So in this first part of the lecture, what we have done is that we have defined the line integral for the motion of a particle or a system of particles, and we have introduced the parametric equation in terms of parameter alpha, which will be varying, and when its value is 0, then we will get the actual path. But so far we have not introduced the variations or the calculus of variations, because the first thing was to introduce this line integral j, and also in terms of parameter alpha. So once we have done this, the next thing is to understand what the stationary points of this line integral j are. So by stationary points we mean that this derivative of j with respect to alpha, and once you have calculated this derivative and after that derivative you put alpha is equal to 0, must vanish. So if these conditions are satisfied, then we say that those points are actually the stationary points, and when the points are stationary for any path, then that path will be the correct path. So this is actually the calculus of variation, or to calculate the actual path. What we do, that we take this derivative of this j, this line integral with respect to alpha, and put it equal to 0, and from this then we will see that the Lagrange equations come out. Okay, so as I said that we have to differentiate j with respect to alpha, so let's do this. You can see here that this j, the value of j was this one, and we want to differentiate it with respect to alpha inside the integral. So f was a function of y and f was also a function of y dot. By chain rule we have to differentiate f with respect to y first and then y with respect to alpha, because y was a function of alpha, and since f was not an explicit function of alpha, it was a function of alpha through y, therefore we had to use a chain rule in the first term, and we also have to use the chain rule in the second term, because f is a function of y dot, that is y dot is the derivative with respect to x, and then y dot is a function of alpha. So you see that this derivative of j inside the integral is actually sum of the two terms. So we have now two integrals over here, this the first integral and the second integral, and it is useful to calculate the second integral first, and then what we will do, we will calculate the second integral and put it back over here in this equation, and then we will see that from here we will get the Lagrange equations. So our task is now to calculate this second integral, and this second integral can be explicitly put into this form. You know that this y dot is a derivative with respect to x, so we can explicitly write equal to del square y del x by del alpha. So this this integral over here is actually equal to, explicitly written equal to this thing, and now it is in useful form, and now we can apply the integration by parts to do this integral. So now let's calculate this integral explicitly, and in order to calculate this integral we need integration by parts. So integration by parts is defined when you have two functions inside the integral. So this is the first function over here, and this is the second function, and you know that when we do the integration by part, we first we first take the integral of the first function and then minus this thing where the derivative first of the second function and then the integral. So this is the integration by parts, and the first term in this right hand side, this one, is actually equal to 0. And why it is equal to 0, this was explained in the diagram in the slides above, where we have said that the y at x1 and x2 is equal. So all varied paths pass through x1 y1 and x2 y2, which means that the surface terms or the boundary terms where all the paths meet pass through these 2 points are equal, and by definition when we put these limits over here, then we will get 2 terms with the opposite signs, and therefore this first term vanishes, and we get this left hand side equal to now to the right hand side, and the only term with a negative sign. So now if we put back this integral into the j, what we will get over here, as we have already got this term by differentiating j with respect to alpha. So if we have now calculated the second integral by integration by parts, and this was equal to this term. So if we put back the integral here, so what we will get, d by dx del f by del y dot, and now this is dg by d alpha, and this is probably in a more suitable form. So this was the end of the second part of the lecture, where we have now differentiated the line integral j with respect to alpha, and we got something like this. But we want the Lagrange equations, we are still away from it, and in order to get the Lagrange equations over here, we have to in order to calculate this, we have to understand one more technique, and this technique is called condition for stationary points. And this condition for stationary points is, as we have already discussed, that when you calculate this integral and you put alpha is equal to 0, then it gives you the correct paths. And now we have to put equal to 0, but when we have put that equal to 0, then on the left side inside the integral, you see that we got the 2 terms, this term and this term. So we have 2 functions, so in these parentheses we have this function and this function, and this is equal to 0, but we don't know which one of them is equal to 0. So in order to know this, we have to go to the technique called fundamental lemma of calculus of variation, and this fundamental lemma tells us that if we have integral of 2 functions, let's say call them m of x and eta of x dx equal to 0, going from x1 to x2, this lemma actually we are trying to understand in order to understand this equation, which is the condition for stationary points. So from here our third part of the lecture starts, where we want to understand this stationary points condition, and in order to understand the stationary point condition which is equal to 0, we are trying to understand this lemma, And lemma generally means that if we have two functions, m of x and eta of x dx equal to 0, then, and these etas are actually arbitrary functions and continuous through second derivatives. So these etas are, if you take the second derivative of them, they are still continuous. So if this is the condition, then this m must vanish. So these m of x, these functions must vanish identically through the interval x1 and x2. So we will not go into the derivation of this lemma, but later in an example we will see that this is actually the case, that when these y of x, which are the continuous functions through second derivative, are there multiplied with the m of x, and this integral is equal to 0, then this m of x must identically vanish. So if this is the condition, now if you go back and compare this with our own thing inside the integral, so you will find out that this m of x actually correspond to this equation, del f by del y minus d by dx del f by del y dot. So let's go back and see if this was the case. Here you can see, so this thing is now our m, this is our m, and this is our eta. So as from the lemma, if this is the continuous function, so we know that this m must vanish. Therefore here in this slide you see that this del f by del y, or this term, these two terms, the subtraction of these two terms is equal to 0. And this might remind you the form of the Lagrange equations, if you as we have derived in the previous lectures. Okay, so once now we know that from this lemma that this gives us a condition that del f by del y and minus d by dx del f by del y dot is equal to 0. So our condition for the stationary points will be different now, and by definition we say that the stationary points will be those points for which these etas, remember these are now kind of these are the etas, these are those functions corresponding to eta, that is del y by del alpha at alpha is equal to 0, d alpha is equal to del y, and we call this del y is a variation. So this is our variation now. So this is an interesting and important point to understand, that these variations from this lemma are now correspond to this delta y. So we define this whole etas, change in this etas or the derivative of this etas equal to delta y, and you will see that for the actual paths this delta y will be equal to 0. And this is the main message of this lecture, that these variations, by putting these variations equal to 0, you can calculate the actual paths of the motion of a particle. Okay, so this differential property represents variation from actual path, as I have already explained. So next thing is that to make this everything infinitesimal. By infinitesimal I mean very, very small. So this is a kind of infinity, by which we mean that the variation is a very, very small variation. So we have an actual path, so consider that we have an actual path between 2 points, and there is a very small variation, we call it delta y, and this variation over here is very, if we put this variation equal to 0, then what we will get the actual path. So this is the whole idea. So let us make it infinitesimal, this variation, and we say that infinitesimal variation about the correct path is this one, that is the delta j, and this was the integral j, and the derivative of this j with respect to alpha and d alpha is now the change in, or the infinitesimal change in the integral by definition, and j is will be stationary for the correct path. By stationary we mean that this delta j will be equal to 0. So whenever j is stationary, which means that this delta j is equal to 0, this means it's stationary, then we will get the correct path. So you see that we have derived the condition or the procedure for obtaining the correct paths, and that is by putting this infinitesimal variation equal to 0, and whenever we put this infinitesimal variation equal to 0, we will get the correct path. So this delta j as you see, was equal to this integral, and this integral is equal to 0. But now we have the lemma that these are the m's and these are the deltas, and from this lemma you know that this will actually give us the equation of the motion. Okay, this was the third part of the lecture, and now in the last part I will give you some examples of the calculus of variation, and I will explain in detail first of them, and the rest of two are left as an exercise or an assignment for you to understand. These are just the similar as to the first example, which I will explain in detail. So the first example is the shortest distance between 2 points in the plane. Can we calculate this using the calculus of variation? This we will see. And then there is another interesting example is of the minimum surface of revolution, and the third example is the Bras-Chestokron problem, and the second example, this one, and the third example, this one, is left as an exercise for you to calculate. And this the first one, now I explain that how we can achieve how we can calculate the shortest distance between 2 points in the plane using the calculus of variation. So the shortest distance between 2 points in the plane, this is our goal, this is our aim to do this. So we define an element of the length in the plane. For example, this is the plane, and in this we define the element of a length, let's say call it delta s or so, and this is the element of the length, and here this ds is equal to dx square plus dy square under the root, and this is the famous Pythagoras theorem you can see over here. So what we are saying that the distance between 2 points is equal to the dx and dy, and this is the distance ds, and if you apply the Pythagoras theorem over here, then this is the length element. Actually this is the length element of length, this one, and this is in the plane, that is in the Euclidean geometry, equal to dx square plus dy square. By the way, if you are not on the Euclidean geometry, as you will see in the other examples, then here you will get the length element differently. Okay, so once we have the length element, then the total length of a curve between any 2 points 1 and 2 will be equal to this line, this integral. So this will be equal to 1 to 2, and ds is the length element. If we integrate this length element between points 1 and 2, we will get the total length, which is equal to this integral I. And we know that this ds value, so let's put the ds value from this equation over here to here, and since we are integrating over dx, so let's take the dx common. So once we take the dx common, so we will get this thing, and now we know that this is the function we want to integrate over dx, and once we do this integration, or once we do the variation and put that variation equal to 0, we should get this straight line. And let's see if we get this straight line. So we have defined the integral. Okay, so that was the recipe. First of all, define the length element, and then define this integral, and next thing is to calculate the minimum. So for this, to calculate the minimum, we have to define a function, and this function we have already defined over here. You can see this is the function f. If you remember, we have defined this integral previously equal to j, and this j was between points x1 and x2, and here it was a function of f, y and y dot and x. So you can see this I actually now corresponds to the integral j, and this is the function, and you see this is the function of y dot, and y is not here in this case, since it's a function of on y dot only. So in this case we don't have a y, so it's a little simpler. But now we have a function f, and we want to know its minimum or its stationary points. So we will take the derivative, because we need the derivatives in the Lagrange equations. So del f by del y is 0, because there is no y, so f is not a function of y, therefore the derivative of f with respect to y is equal to 0. And then the derivative of f with respect to y dot, if you do the derivation, you take the derivative of f with respect to y dot. This is a very simple calculation. So what you will get is y dot 1 plus y dot square under the root. This is a very simple calculation which comes from here. So we have calculated the two derivatives, and the next thing is to put that into the equation. You remember del f by del y minus, so del f by del y is equal to 0 minus d by dx, and this is the derivative here, del f by del y dot, and this is equal to 0. And if this whole equation is equal to 0, that is the derivative of this function over here is equal to 0, that means that this function inside the parenthesis must be constant, and let's put that is equal to constant c. So that it gives us y dot over 1 plus y dot square under the root is equal to c, some constant. And we can further simplify this equation by saying that this y dot is equal to some another constant, and where a is a constant related to c as equal to this one. A is equal to c by 1 minus c square. And from this we see that this is actually giving us the equation of straight line. If you take this onto the other side, what you will get that y is equal to ax plus b, and that is the equation of a straight line. And that was our goal, if you remember, that we had different paths as was explained earlier, that these all paths pass through these 2 points, but none of them is a correct path. But we know that whenever particle moves from this point to this point, it will follow actually a straight line. So it will follow a straight line, and this was the result of this calculus of variation. It gave us the straight line. So in this case over here, then we will get a straight line, and this orange line is actually the path of the particle, which comes out from the calculus of variation. So in today's lecture we have actually divided into 4 parts, and this was to learn the calculus of variation and its main technique, that is the calculating the correct path or the actual path of a particle or a system of particles whose motion we are considering. And for that the first thing is to define the line integral, and once you know the line integral, the next thing is to find out define these functions inside the line integral and make them dependent on some parameter. And once this is done, we have to calculate these derivatives of this function, and have to find out the minimum of that function. And once we know the minimum, we are able to use the calculus of variation, and this calculus of variation tells us that if infinitesimal variation of this line integral is equal to 0, then we will get the condition for this condition for stationary points will give us the correct path. And then we have used one example to illustrate this whole procedure, and that was the path of a particle in a plane. So I hope you have got the idea of a techniques of a calculus of variation. Thank you very much.